Well, thank you very much for the introduction and for having me. For me, it's been a long time to be at a conference, but unlike some other people, for my work, it's actually to our advantage that our last conference was 4 years ago. I'm glad this conference is only once every 2 weeks, or 2 years, because it's slow progress. And it's because it's low temperatures. And this is the group that's working on it currently, so we're in the third row. And Jason has recently left our group, graduated. She now works in Dell, but she's also at the conference. And she organized the online version together with some other graduate students. So we did have something. Plus, there's a lot of technical work that goes into these experiments, and I only show the ones that are currently working, and I listed some companies, and I'd like to point out that for us, thermometry is very important. You know, sometimes they say a physicist with a thermometer is a happy physicist, but a physicist with 2 thermometers has problems because they don't indicate the same temperature. And actually, this company, it's actually one person, Wim Bos, and he makes very accurate, very fast thermometers between 10 millikelvin and 1 Kelvin. And then it's a pain to have many accurate thermometers because they all indicate different things. But if they're fast, you can actually see and figure out what's going on. And this has been very important to reach the ultra low temperatures. And then the companies in red, I have a financial interest in, so don't really have anything to say about this. A few years ago, the group was larger, and the graduate students were leaving one by one, and I didn't have any new funding to replace them. So I was down to one graduate student, and I asked him, please teach me everything about all of our equipment, because soon there would be no one to run it after you leave. And then he taught me, and thankfully he also instructed the new graduate student, because some funding did come. But I knew how to operate the equipment, and then Corona came, and no one was allowed in the building, except maybe 1 or 2 people, because there's this helium-3, and you know, if you lose all of that helium-3 because no one watches it. So I've been able to do a lot of experiments recently. And then this is longer ago, and maybe you recognize Sasha Usenko and Theo Vinante were at the very earliest. And this is kind of the thing in 2008, where I very generously was led into the field. And then when I said, hey, I'm going back to Leiden, and we like low temperatures in Leiden, he said, don't do MRFM at 10 millikelvin, don't try it. I mean, it's so hard to do it at 220 millikelvin, as he showed. And so, you know, it's a large responsibility to ask Dan what not to do, because then, if you do what he advised not to do, it will take a very long time. Because it seems like a good idea to reduce the temperature and get the noise down and get you know, perhaps continue to have the same signal, but get the noise down would be really nice. So then you have to maybe lower the friction of the cantilever, but actually, if you go to lower temperatures, I was hoping that perhaps it would, you know, do away with the electric field noise, because if you freeze everything thoroughly, maybe you don't have this non-contact friction anymore. Because if charges don't jump around because the temperature is just so low, of course charges continue to tunnel if they get a chance. And we actually found that all the gain in temperature we achieved was compensated by an equal increase in friction. So the product of the two, was T times gamma was still the same. So why go to low temperatures? Well, maybe because you're stubborn and you're less capable to admit defeat. But there are some other things. You might hope that at very low temperatures, the polarization of the electrons with the field would be better. So if we say HF is KBT is UB. Those are the energy scales I'm comparing. 1 Kelvin is 20 gigahertz. It's about 800 millitesla for electrons. But if you go 100 times colder, or maybe 1,000 times colder, if you could, then nuclei become polarizable, and maybe that will help to increase the signal. And then recently, with the work on quantum mechanics and all, we can hope to reach a new regime where the quantum coherence of the force sensor might enter the millisecond regime, where it's the cantilever tau divided by the number of phonons in the bath at this frequency, which is basically KBT over HF. And so HF is 200 megahertz, and then if you have a force sensor at 2 kilohertz, you would have to divide your cantilever tau by 100,000, which is a really short time. So very quickly, the quantum effects of your force sensor would go away. But if you wanted to study whether a quantum or a force sensor, like the NanoMRI7 force sensor, maybe it is a quantum object and it can be in superposition of different positions, then from this number it's obvious you have to go to a millikelvin or lower if for a low frequency NanoMRI7 kind of cantilever to see quantum effects with that. But if you could, that would make for a very heavy object to be displaced by quite a large distance. Because if your Sprint's constant is low, you can displace it with the interaction of an electron and maybe really learn something new about quantum mechanics and the measurement problem and all the nice stuff there is. So if you ask me why am I willing to suffer for another 20 years, that is the reason. So, I think that is a problem people think about, and it's a problem that it's okay to be behind the horizon. And it's something nice to strive for. And recently, I see that it's actually possible to get money, research money for this. So previously, I had to work on NanoMRI because that would be a big payoff, and I get money for that. And now I can also get money for quantum things. So even without writing more than 1 or 0 papers per year, you can still get money for this technology, which is difficult for the PhD students. But that, it started with, let's remove the laser to not have excitations in the surface that cause non-contact friction. If you have a cascade of energy, maybe the charges move around, and that could be the source of the friction. That was my initial motivation, to do away with the laser. And actually, we use a squid to detect the motion of the force sensor instead of the laser. And then, if you want to generate RF pulses, so make the magnetic field, you have to send a lot of current, and that would generate a lot of heat unless you use a superconductor. That's the idea. And this is the kind of things we strive for. So if we can keep the magnet on the cantilever, then we could use more general sampling. So maybe have slices of biological material in the far future. But the real reason that allows me to continue this hard work and with slow payoff is the quantum. So here you see our measurement setup, where one feature is that we can inject some current in this loop, and then we can not only calibrate the sensitivity of our flux readout, we can also calibrate with how much force we need to drive the cantilever to see a motion. So it's a calibration in energy that is quite absolute, which is nice. And the noise of a squid, this is the squid, is measured in microfinals, which is 10 to the minus 21 Tesla meter squared. So that's a really small number. And that means we can give away a lot of things and still have sensitive readouts. And the squid, of course, operates at really low temperatures, and it doesn't talk back too much noise. Now, the problem with the squid is that it's sensitive to all magnetic fluctuations, so we had to think from the beginning, how do we shield our experiment so no magnetic flux comes in. So everything is packed up in the superconductor, pneumatic shields, and all kinds of things. And then to do the scanning, we have to make sure that no noise from our piezo elements is reaching our sample. So there are lots of little things. But, wow. Here you see how our magnet approaches the sample. Right? And then that's what we do as a measurement. We also worked on a cryogenic positioner for a while. And I think I showed this slide 4 years ago, and now I'm showing this slide. So we spun off a new company that I have financial interest in. And AutoCube having a booth here, I brought some leaflets that I will try to sneak on the AutoCube booth. So when we talk about the sensitivity for nuclei, we have several problems to solve, and so 4 years ago we reported on the vibration isolation that makes this MRFM work even in a dry dilution refrigerator. So we have compressors in and we can still do MRFM thanks to this vibration isolation. And we found perhaps a solution to the problem of creating B1 field oscillating. So we have the low temperature, good detection sensitivity, and when we approach our surface, we now have to put our sample right next to this pickup loop. So if we want to study a sample, it has to be close to this pickup loop, otherwise we can't even see the motion of our force sensor. It also means that when you initially start the experiment and you have no signal, you're really in trouble, because you have to blindly find the place where this cantilever maybe has some signal. And then once you have it, you're found that you're close to the pickup loop. So that's really the downside of not having a laser, which is always aligned with the force sensor. But now that we have this vibration isolation, and once you have found the place, then you can return to that place. Sorry. So this is what our vibration isolation looks like. And in the past, we would have to zoom in and in a zoo of little peaks find our cantilever. And that is because this squid is sensitive to any flux variation that is tiny. And if some magnetic screw somewhere is shaking at a particular frequency, that will generate a peak in this spectrum. But later, we figured out how to do away with these vibrations, and then we could do atomic resolution STM inside a dry dilution refrigerator. And things have cleaned up also in the spectrum. But it was very important to learn how to weld copper, for example, such that these different masses are really thermally connected really well. And there are some tricks in this, because you want to weld all the copper wire without melting your setup. Of course, this is still done in the workshop. But then after this deploy, we now have the spectrum where we only see the 50 hertz and multiples of 50 hertz that we did not clean up properly, which is a disgrace. The B1 field, we ran into a coincidence that actually it's possible, and this is the lowest mode, but then you have higher modes that actually oscillate at much higher frequencies. They rotate the magnet at the end of our tip, and this rotation causes a time-varying magnetic field that is exactly perpendicular to the B0 field in our sample. So that means that you have a source there of RF at all of these different higher modes. And then we can do we can do MRFM with this on copper. But as we come closer to the surface and we were studying copper, we also saw that Q factor collapses because of the eddy currents of the sample we're studying with the magnet. So, but at least we can, with different modes, have these slices move through the copper one by one, and we think that this is a proof of that we can measure, despite these low temperatures, the nuclear magnetic resonance of the copper atoms. And after the thorough analysis, we see that the B1 field is still too low to do adiabatic rapid passages. So you can only do saturation in our. The noise is pretty low. I mean, the units here are millihertzes, and our cantilever is kilohertz. So this is really the sixth and the seventh digit of our mechanical resonator. And we would love to be able to measure the force, but for that we need larger B1 field. So that is the nuclear part. I would like to go to the electron spin part, and I'm actually going to skip the part where the polarization of the spins on the surface is our source of dissipation. Because we can do magnetic resonance on those surface spins and do ESR. But the trouble is that when this cantilever moves back and forth, and it has spins that are polarized by this magnet, if the magnet of the cantilever moves, then the spins feel a field at a slightly different angle, and they want to adjust to this new field, and that causes dissipation. The T1 time of these spins is similar to the oscillation period of the cantilever, and because we are at such low temperatures that these spins are polarized, we suffer from dissipation. Now, when we wrote this paper and claimed this, then the referee said, well, if you're sure these are magnetic spins, then why don't you switch on the magnetic field and prove to us that it's spins? And thankfully, the referee let us publish without this easy extra experiment, because if we apply a magnetic field, our squids don't work anymore, and maybe our vibration isolation won't work anymore. So we're still living under the assumption that it's surface spins. Although, I mean, our models describe bulk spins, surface spins, and we can actually say, hey, it's not a bug, it's a feature. We can measure your surface spins for you. If you give us your devices before and after fabrication of your qubits, we can measure the surface spins that cause your qubits to have a low T2 time. But life would be much better if we could apply this external field. What we did to prepare for qubit people that suffer from surface spins is a device where our pickup loop can be right next to the force sensor, hoping that we can study different surfaces. So it's something that is starting to work better and better. But what we'd rather do is have an external field and do away with this surface spin dissipation. What we also would like to do is have the beautiful force sensors that the Degen group makes, and some other things that we tried. So with the Degen group's surface spins, so Martin Etier came to our lab, and together with Geja Welker, we will present a poster tomorrow. Well, we hope that also better force sensors than the IBM style force sensors will help us in the future. Another thing is that we lower the temperature below that of the dilation refrigerator. So this is 10 or 12 millikelvin. Inside this magnet is praseodymium nickel 5 that makes these silver wires cool down to below 1 millikelvin. And we put an experiment right next to here, and then we tried, and we saw a cantilever go to a higher Q, lower dissipation once, and we reached 6 millikelvin at a time. And then Martin de Wit famously removed the cables that powered this magnet to Tesla and said, we will not do this in the time that I'm a PhD student, because we will do some thing that's maybe not so difficult. But Corona, well, his graduation plus Corona helped me try something new. And that is that we take a silver wire from this experiment upstairs down alongside the mass spring system. And there was a paper 2 years ago around Christmas that Lego blocks have very low e-conductivity. Did anyone read that paper? Because it was read by 100,000 physicists. So well, I'm glad a few hands were raised. The Lego blocks help us, and it turned out that the important thing, I did not include that picture. The important thing was that we had to learn how to weld inside the cryostat. So we don't go to the workshop to connect a piece of silver to another piece of wood silver. We take a welding machine to our dilution refrigerator and we weld it right there. Because clamping one piece of silver to the other prevented the lowering of temperature. And then we do the thermometry by winding a coil around a piece of silver, and we measure the flux noise that the moving electrons induce in this coil. And we use equipetition again, and in that way we know the temperature. So here's our tribute to the anti-war effort. You measure the noise of the flux in this coil, and you calibrate it against a normal thermometer. And if you have this calibration right, you can then say, okay, when we were really cold, we had much lower noise in this thermometer, so we can reach temperatures of 1 millikelvin approximately. And if someone slams the door, you see the temperature have a little spike. But there's actually a lot of heat capacity in this praseodymium nickel 5, and then if we then warm up, it goes quicker. And the nice thing is that we now have measurements of our force sensor. This was the first run in which we were really far away from the surface, and I was happy to do these experiments, and I thought, okay, next time I will do a better job. And actually, that's why we are at 1.5 millikelvin, while I think if I had more patience, we could have gone a little bit colder on this run. But it's nice to see that the Q factor continues to decrease, and it's a signal that our cantilever is responding to this lower ring temperature. And in the next run, we will do this experiment to check whether we can actually measure the thermal noise. But for that, we should also cool down our sample, because our sample determines the Q factor, and then the sample temperature is as important as the cantilever temperature. And I'm hoping that we can reach a new level of force sensitivity. But yeah, so far it's not completely done yet. However, we also like to generate larger B0 fields externally to pay our dues to the referee that was so gracious to let our paper pass without generating this B0 field. But I feel, okay, there are two problems. You know, usually you just take a big magnet bore and you make your a uniform magnetic field everywhere. That would be, our scripts would not like that. And we found a solution where we make our magnetic field with in a very small volume, only a few cubic millimeters. And then you don't need as much energy that you need to put into that coil, because it's proportional to the volume. So if you do square centimeters, it's 1,000 times more energy than a square millimeter. And we found a material that makes for good transformers even at 10 millikelvin. So these are voltage pulses that charged a very small coil through this transformer. And we have a second transformer. Here you see a twisted pair of superconducting wire that becomes normal because it's inside this core. And that is together, it's called a persistent mode switch. So that, and then I'll do this last thing in 2 minutes, it sets the stage to do future quantum experiments with these type of cantilevers. So we would like to know, hey, is our force sensor something that can be brought in superposition, or is it a piece of measurement apparatus that only gives one measurement result if it's confronted with two magnetic fields? And this is inspired, of course, by what David Baumeister, who is another department. The idea is that if our spin interacts with our force sensor, how can we generate a superposition with as little RF power as possible? And the scheme that I could think of that needs the fewest RF power is one where you drive the force sensor and you use a frequency shift due to the interaction with the spin. And then if you bring it in superposition, with one pi/2 pulse, you get a superposition. But one will have a spring hardened cantilever and the other is spring softened. So they will have a different position. So after some time, the cantilever is brought in superposition, and the cantilever on the left is associated with the spin up, and the cantilever on the right is associated with the spin down. So I can give a new pi/2 pulse and bring it in superposition again. And that is kind of a double slit experiment where there are multiple paths to end up in position 2. And some of those paths will interfere constructively, while other paths will interfere destructively. And then the experiment would be you have to measure the probability to end up in one position or another. And if that is affected by interference, you have shown your force sensor was in superposition a long way. So this was originally the idea. We need this to be a very high Q resonator, and we need it to be very cold, because if the phonons in the bath talk to this force sensor, you will lose your coherence right away. And in the other sense, if the force sensor talks to the bath, it's a which path sensor, and your coherence is destroyed. But if we were, somewhere here, we just start to see this interference. So for that, we will need, however, the collaboration of many people in this room, because we need better magnets than we are using in my lab. So we already had dinner with John Marone, but my group members, they all were late, so they sat on a different table, and we have to have dinner again because we really need to meet my group members. Sorry. So there are a lot of important things, and this is kind of the thing that we're now getting very, very high purity diamond from Delft, the group of Ronald Hansson, but also Timo van der Sar has been teaching me things I did not know about NV centers. And we also managed to incorporate niobium coaxial cables, and this sample holder is niobium, and it can make this millimeter cube magnetic field for us. And so then there is a transformer, and here's our split. So these are all the ingredients in place now to hopefully, after 10 years, repeat the single electron spin experiment. But then in a situation where we have a chance of, in the future, if we continue our perilous way, slow way forward, and we reach maybe 0.5 millikelvin, and if indeed the measurements we have done on the dissipation of this gigahertz setup, then I think I'm starting to believe that before I retire 20 years from now, we have a chance of trying these type of experiments. And I hope to meet you once every 2 years to report on future progress. And this is Tim's poster tomorrow. But thank you for your attention.
Tjerk. We have plenty of time for questions.
You can also ask me in 2 years.
So the quantum random walker distribution you were told, right? That again, it has the maximum in the outside, right? So you expect to have unless you're point must be some strange things.
Yeah. So you really need to control your spin very well, and in the end, that is what your spin will have to have the same coherence time as the cantilever at least. So we're talking about 10 milliseconds. That's kind of the goal we're aiming at for both the coherence time and for the coherence time of the spin and the coherence time of the cantilever.
Usually assume a coherent superposition.
Yes.
You just assume a coherent superposition, right? Of the spin. Then I'm wondering why it's not the extreme on the outside being maximum, because that's what I typically would expect from
there are 3 ways to get here and 1 way to get here. So basically you have this 3 is 1 plus 2, unless it's constructive interference, and then it's 1 plus 4. And this will be 1 plus 0 if this is destructive interference. So the interference only happens on the inner 2 paths, because there is a way that you have identical spin at the end and identical cantilever position, and then you can have interference.
Okay. Yeah, thank you.
Questions?
I'll just speak after. Your guy obviously understands the experiment better than I do. What are you measuring? what's the signature?
The signature is the interference of the final position of the cantilever.
What does that mean?
So we prepare the cantilever in a state, then we switch
State
off.
meaning an oscillating phase?
Yeah, it's an oscillating state that we know amplitude and phase very accurately. We switch off the squid, we no longer measure the position, then we do a sequence of pulses, and then we start measuring the position again. And then we have 4 possible positions of that the cantilever can end up in after we give this sequence of 3 pulses.
So you measure 4 different amplitudes, or
And then we will
phases? Or?
4 different phases. Yeah, and that phase means it's in a different position, and it just continues to oscillate at this.
And then you repeat it over and over again and build up your
And
statistics.
you do that experiment 10,000 times, and you will get a histogram. If this histogram has this asymmetry in the middle, that would be a sign of.
And do you have to turn the measurement off during is there some evolution time?
So during this time here, vertical, you have to not measure the position of the force sensor. And then we can achieve by switching off the squid. And while normally we continuously measure the squid output, and from that infer where the force sensor is.
Thanks.
So now, if I may, I'll ask some grungy technical questions, just because I'm curious and ignorant. So, 1, the welding for the silver. So what goes on to clamp? Is it some work function issue that gets in the way of
I think it's oxides.
oxides?
And the problem is that thermal conductivity is proportional to the electrical conductivity times the temperature.
Uh-huh.
And the lower the temperature, the lower the thermal conductivity is. And to double the temperature, you need a much smaller temperature gradient.
Yes.
And so it's very, very easy to double the temperature if you're at 1 millikelvin.
Yes.
And it's much harder to double the temperature if you're at 4 Kelvin and you're sitting in a liquid helium bath.
Okay, thank you. Second grungy technical question. I'm just curious about this magnificent transformer, the core, whose permeability remained very good at super low temperatures. What was that material, and how did you know it was going to?
It's called met glass.
Met glass, yes.
It's a metallic glass because they
Sinter.
have a cold wheel and they jet liquid metal on it. So it is a very thin string of metal that cooled down so quickly it had no time to form crystals. And then we just tested it.
You just tested it, yeah.
But people had done it in conjunction with bolometers readout. They used this material.
Okay.
So we knew it should work, and it worked much, much worse than they said it would work. But it worked even at 10 millikelvin. So, you know, we're happy. It's not 10,000, but it's 100
Yeah,
or
sure.
300. That's
Sure.
plenty.
Okay, thanks.
Any other questions?
You have the question?
Okay.
Well, thank you for the great talk. Just a quick thing, I think I missed it, but what is exactly the magnetic field you're using through this technique? And the second question related is, since you're such low temperatures, are you actually looking at thermal polarization, so statistical polarization?
So we will look at thermal polarization generated by just the magnet on the tip. So our magnet on the tip is neodymium iron bore, which has 1.4 Tesla. And so if you're one radius away from it, from that surface of the magnet, you're at 1/8 or 1/16 of that magnetic field. So we work at approximately 100 millitesla, which is the equivalent of 100 millikelvin for electron spins. But it means we have 1% polarized blah 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 of nuclei, because they're at 10 millikelvin, we have 1% proton polarization.
So you are looking at thermal polarization, and that provides a signal to noise ratio.
Yeah.
Okay, I think we need to move on, so let's thank Tjerk again.